Hi everyone, and welcome to today's webinar about the setup and modeling of a reactor and turbine trip. To introduce myself, I'm Barney Meiren, one of the simulation design engineers at Flownex, and I will be presenting this webinar today. The co-authors who helped me create this webinar are Ruth Lawrence and Vincent Britz. Both have years of experience consulting nuclear research and development facilities. Before I continue, I would like to explain the webinar interface and how to ask questions. You will see a question tab on your right hand side, and please feel free to type in a question at any time during the webinar, and we will answer all of your questions at the end. For today's agenda, we will look at the importance of accident scenarios, why a 1D simulation tool can assist you in modeling accident scenarios, a quick overview of how the model is simulated, the setup of the transient accident scenario, and the result obtained from the simulation. Accident analysis of a nuclear plant design is crucial for licensing and forms part of the safety analysis report. Such an analysis showcases the capability of the safety features of the proposed plant to prevent an accident or lessen the effects thereof. A few examples of common accident scenarios that should be tested are a depressurized loss of forced cooling, pressurized loss of forced cooling, loss of cooling accident, steam generated tube rupture, loss of feed water, turbine trip, reactor trip, etc. This creates a need for a computer code capable of simulating such nuclear plants, the reactor and the power cycle with all of its components in steady state and transient. 3D CFD computer codes often take a very long time to solve or focus on specific elements of a nuclear system and require a lot of computing power. However, 1D simulation tools can simulate larger systems much faster with much less computing power. Yet, one of the limitations of many 1D computer codes is that they are limited to only reactor modeling or only power cycle modeling. Flownex, however, has the capability of modeling an entire nuclear plant from the reactor up to the power cycle. The simple nuclear plant used to model an accident scenario for this model will consist of a primary loop and a secondary loop. The model was kept simple for demonstration purposes, but Flownex is capable of modeling large integrated systems, and I will show some examples at the end of the webinar. The primary loop will consist of a helium-cooled prismatic block reactor, the helium circulator, controllers, and a helical-cooled steam generator. The prismatic block reactor and the setup thereof was discussed in detail in one of our previous webinars, so feel free and go watch the recording on our YouTube page after this webinar if you need any additional information about this. The secondary loop consists of high pressure and low pressure turbines, a Deaerator, condenser, feed water heaters, a feed water pump, a condensate extraction pump, control valves, and controllers. Here is the model with the primary loop on the left hand side and the secondary loop on the right hand side. The primary loop uses helium as the working fluid, and the secondary loop uses water. This is the helium-cooled prismatic block reactor to model heat generated through fission and the transfer thereof to helium. This is the helium circulator used to model helium circulation through the reactor and steam generator. This is the steam generator to model the heat transfer between helium and water. The modeled reactor is a prismatic block fuel reactor. The core consists of prismatic blocks with patterned holes or channels for cooling or fuel slots. On the right is a representation of how such a prismatic block looks like, and on the left shows the dimensions of the reactor. The bottom right is a section view of how the blocks are arranged to complete such a reactor core, consisting of fuel blocks, control blocks, and graphite reflector. The reactor core is surrounded by a core barrel a reactor pressure vessel, and a coolant annulus in between. The reactor setup was explained in detail in our previous webinar, where ANSYS space claim was used to calculate the required flow and heat transfer geometry from a CAD file. These parameters were written directly to the reactor geometry editor in Flownex, eliminating the need for any user inputs. We can model different steam generator types. The one we are modeling in this webinar is a helical-cooled steam generator, similar to the design used in the thorium high-temperature reactor plant. The steam generator is modeled with a composite heat transfer component, which models the convection on the fluid side and conduction through the pipe walls. The composite heat transfer component provides the user with the freedom of using your own custom heat transfer correlations and pressure drop correlations. Otherwise, you can just use the default component settings. The shell side is modeled by specifying the flow area, the hydraulic diameter, and the length of the shell. The tube side is modeled by specifying the tube's length, diameter, and the number of tubes in parallel. The pipes representing the tube and shell side are incremented as well. In the background, the pipe and respective convection and conduction resistances are discretized as seen in the figure on the right. This means that convection is calculated at each of the specified increments, along with the conduction and cross-conduction through the pipe wall. This allows the software to accurately capture the wall temperatures during boiling, which is essential to accurately capture two-phase boiling physics. Here you can see the effect of all this in the comparison of a Flownex model of the thorium high-temperature reactor steam generator to measured data from the plant. You can see a good agreement at both full power and 40% power, where the lines are the Flownex data and the circles and crosses is measured plant data. Next, we will look at the secondary loop, the Rankine cycle. The high pressure and low pressure turbines are connected to the same shaft. With this component, the total power generated can be calculated and the speed can be calculated during startup to simulate synchronization with the grid. The Deaerator and condenser are modeled with two-phase tanks, so that the phase change of the water and the level in the tank can be tracked throughout the simulation. The two feed water heaters are modeled with composite heat transfer components to model conduction and convection. The feed water and condensate extraction pumps are modeled with basic pump components. With these components, the required volume flow and head can be calculated for specific mass flow. The speed of this pump can be changed dynamically in transient to simulate the changing performance of the pump at different operating speeds. The valves for the steam extraction lines were simulated with basic valves and were sized for the required steam flow rate needed for an energy balance. The turbine control valve and the bypass line valve are modeled with basic valve components. These components can be used to calculate the valve's flow coefficient for a specific mass flow. The opening of the valve can be controlled dynamically as well with the PID controllers in a transient simulation. And the steam generator as discussed previously. We will now have a look at how the plant is controlled from transient simulation. Under normal operation, we have chosen the following control pairings. The speed of the feed water pump will be adjusted to control the steam generator outlet temperature. The speed of the helium circulator will be adjusted to control the main steam pressure. The control rod depth will be adjusted to control the reactor outlet temperature, and the opening of the turbine control valve will be adjusted to control the generated turbine power. We can model all of the details of a full control system, including the digital control used for different operating modes. Still, we have chosen to only model the control on the high pressure side of the Rankine cycle and the primary loop to keep the model simple for this demonstration. Next, we will discuss how to use this model to simulate a reactor and turbine trip. A reactor trip usually follows after undesired or offset conditions in the primary loop or reactor, which leads to the need to initiate the scram, followed by a turbine trip. In reality, the events that trigger a reactor trip and the actions that follow are very complex. For this webinar, we have simplified this in a few key actions. Actions were set up to apply changes at specific times during the simulation. After 60 seconds of the simulation, a scram was initiated where all the rods were inserted in the reactor to shut the reactor down. 10 seconds later, the helium circulator was tripped and ran down to a constant speed. 30 seconds after the reactor trip, the turbines were tripped. At the same time, the turbine control valve closed and the bypass valve opened to divert the steam to the condenser. The main steam pressure control was switched from adjusting the circulator speed to adjusting the bypass valve opening. The time step size was decreased during the valve closure for the solver to capture the sudden change in fluid and flow properties. The time step size was increased 5 seconds later, giving the simulation adequate time to stabilize. Now let's solve the model and look at some of the results. Here we can see the control rod position and reactor outlet temperature. And we can see how the control rod depth is changed to control the reactor outlet temperature at its set point. And at 60 seconds, we can see that the control rod depth positions increased due to the reactor scram. To save some time and allow us to discuss the complete set of results, I'm going to stop the simulation and load the final set of results. The transient was run for 6 minutes simulation time, and it took about 6.5 minutes to solve on a desktop computer using time steps of approximately 100 milliseconds. From the reactor outlet temperature and control rod depth graph, we can see that after 60 seconds, the rods were fully inserted in the reactor. During 60 and 70 seconds, there is a small decrease in reactor outlet temperature due to a decrease in reactor power. After 70 seconds, we can see an increase in outlet temperature until a maximum is reached at 210 seconds. The increase in temperature resulted from a decrease in helium mass flow due to the circulator trip and rundown. After 210 seconds, the reactor outlet temperature starts to decrease, resulting in a maximum outlet temperature of 774 degrees Celsius. The main steam pressure and circulator speed graph shows that after 70 seconds, the circulator speed starts to decrease until 200 seconds, where the final operating speed of 5000 rpm was achieved. A speed of 5000 rpm was chosen to ensure a low helium flow through the reactor to remove the decay heat. From 70 seconds to 90 seconds, it can be observed that the steam pressure started to decrease due to a decrease in helium mass flow. At 90 seconds, the control of the steam pressure switched to being controlled by the bypass valve. The pressure response after 90 seconds will be discussed when we look at the bypass valve and steam pressure graph next. From this graph, we can see that after 90 seconds, the valve started opening and took over the steam pressure control. There was a sudden increase in pressure after 90 seconds due to the turbine control valve closing. The control of the bypass valve started to respond thereafter and opened the valve rapidly. The pressure decreased once the bypass valve had opened sufficiently and the valve could adequately control the steam pressure to a value of 16 MPa. it can be seen that the steam pressure reached a maximum of 17.8 MPa and returned to its set point shortly thereafter. Looking at the main steam temperature graph, we can see that after 70 seconds, the steam temperature started to decrease due to a decrease in helium flow through the steam generator. After 90 seconds, we see a steep increase followed by a decrease in steam temperature. In this period, the turbine control valve closed, which led to an increase in pressure and increase in temperature. The decrease after the peak resulted from the bypass valve opening, decreasing the pressure. After 130 seconds, the steam pressure started to stabilize, after which the feed water pump could adequately control the steam temperature around 550 degrees Celsius. From the turbine power and turbine control valve opening graph, it can be seen that the valve fully closed after 90 seconds and the turbine power decreased thereafter. Now that we've seen how the plant responded after the reactor and turbine trip, we can quickly have a look at what happened within the reactor in terms of reactivity, power, and temperatures. The reactivities graph shows the different reactivities present in the reactor over time. After 60 seconds, we can see a steep decrease in control rod reactivity, which is the main drive between the negative reactivity in the reactor. This is to be expected from a scram. The reactor power graph shows the fission power, decay heat, and total power. After 60 seconds, we can see a steep decrease in power, which resulted from a decrease in reactivity. After 80 seconds, we can see that the leftover decay heat mostly drives the total power in the reactor. This means that helium flow needs to be maintained through the reactor to ensure that the temperatures in the reactor don't increase. The reactor temperature graph shows the temperatures of the different solid materials in the reactor, such as fuel, moderator, and reflector temperature. After 60 seconds, we can see a decrease in moderator and fuel temperature, which is expected due to decrease in reactor power. The temperatures kept on decreasing due to the fact that by running the circulator at a constant speed, the flow of helium was maintained through the reactor, aiding in removing the generated decay heat. This simulation can be run for longer to investigate how long it takes to reach a point where actively removing heat is no longer required and the circulators can be shut down. Such simulations are a good tool to investigate whether the safety systems in your plant design can keep reactor temperatures in a safe range and maintain safe conditions in the steam generator. As I mentioned, the model shown in this webinar is a simple nuclear plant. Flownex can model complex systems as seen in these following examples. The first example is a more detailed IP and LP steam turbine train model with gland seals, leak and extraction lines. The second example is a detailed boiler model that uses an XL component in conjunction with flow elements to capture detailed boiler performance based on flame conditions and steam requirements. Here is a list of some of our existing clients in the nuclear industry. Our clients use Flownex for a variety of applications that include power cycle concept design and preliminary plant component design, conceptual designs, studies of different RCCS configurations, pneumatic fuel handling systems, operational transient analysis and control system development, and accident scenario analysis. Some important capabilities of Flownex in the nuclear industry. Flownex can model different fuel geometries such as pebble, block, and rod, and different coolant types such as molten salt, gas, water, and liquid metal. Flownex uses a point kinetics model to calculate the heat generated within a fuel Alternatively, user-defined C# calculations or coupling with external Neutronix code can be used to describe the heat generated as well. As mentioned earlier, Flownex is capable of modeling large integrated systems, which includes the integration of reactors and power cycles. And Flownex provides fast solving speeds and accurate results to help fast-track the analysis of crucial transients spanning over long periods of time. And lastly, Flownex can be used to aid in licensing of new nuclear plant designs, as it is developed within an NQA1 and ISO 9001 environment. To summarize, we looked at an overview of the different accident scenarios and the need for 1D simulation tools. Next, we discussed which components should be used to build a nuclear plant in Flownex and how to configure a reactor and turbine trap. On the steam side, we saw a maximum temperature of 565 degrees Celsius and a maximum pressure of 17.8 megapascal at the outlet of the steam generator. We could see from the results that the maximum reactor outlet temperature of 774 degrees Celsius was obtained during the accident transient. This is crucial information to pass on to the teams overlooking the design of the steam generator and the turbines to ensure that the components will not be damaged or fail during an accident scenario. We also looked at the conditions within the reactor and saw that the negative control rod reactivity was the main drive in total negative reactivity in the reactor. This led to a loss in fission power with only decay heat left over. We saw that running the circulator at low speed was sufficient in removing the decay heat and that the temperatures safely decreased over time. If you are interested in how the prismatic block reactor was set up and how a depressurized loss of forced cooling accident scenario was modeled in Flownex, please feel free to have a look at our previous webinar on YouTube. If you would like to have a more detailed discussion about modeling your specific plant in Flownex and the analysis thereof, go over to the Flownex website and request a demo under the Contact Us section. We will arrange a personal meeting where we can discuss your simulation need in more detail and showcase capabilities specific to your plant design. Alternatively, you can reach out to us by sending an email to inquire@flownex.com. And this brings us to the end of this exciting webinar. Thank you for joining, and I hope that this has given you a better overview of Flownex and its strengths in understanding plant response through various accident scenarios and operating conditions.